All right, let's dive into something you probably use every single day, but have never actually seen. We're talking about the secret mathematical engine that pretty much runs our entire modern world. It's called numerical methods, and it is everywhere, from your weather app to the wings on a jet. So, let's pull back the curtain.
I want you to pause for a second and think about all the math you've ever learned. Algebra, geometry, calculus, all of it. Now, what if I told you that for most of the really messy, really important problems in the real world, none of it is enough?
Hey, don't just take my word for it. This is a direct quote from engineer Johan Larsen. It's a pretty startling thing to hear, right? But it's the absolute truth, and it's the whole reason this other kind of math, numerical methods, even has to exist.
You see, the math we learn in school is, well, it's beautiful, it's elegant. It gives us perfect, exact answers. But it only works for perfect, well-behaved problems. And let's be honest, the real world is almost never clean or well-behaved.
Yeah, this is what we're actually up against. Reality looks a whole lot less like a neat quadratic equation and a lot more like this messy beast. There's no magic formula you can just plug in to get a perfect answer here. This is the kind of math that describes how water flows or how financial markets move. And this is where that perfect school math just hits a brick wall.
So what do? Just give up when the neat formulas don't work? No way. We reach for a different kind of toolbox. And that toolbox is called numerical methods. It's a totally practical, powerful way to wrestle with all the complexity that traditional math just can't touch.
So what are they really? Honestly, the best way to think about them is like a recipe. A numerical method is just a simple, step-by-step process that a computer can follow. And here's the key. The goal isn't to find the one perfect, exact answer. The goal is to get incredibly close.
Okay, let's actually open up this toolbox and grab our first tool. This one's called root finding. The idea here is pretty simple, actually. We're just trying to find the value of x that makes our equation equal 0. It's kind of like we're homing in on a very specific target. Visually, it's this simple. You've got a curve on a graph. Where does that curve cross the horizontal line, the x-axis? That specific point, that's the root. Now that sounds easy, but for those messy real-world equations, finding that exact spot is a massive challenge.
And get this recipe for finding a square root is ancient. It's literally over 3,000 years old. The Babylonians would just guess an answer. Then they'd plug that guess into this simple little formula to get a better guess, and then they'd do it again and again. This process, repeating a simple calculation over and over to get closer and closer to the real answer, is called iteration, and it is the absolute heart and soul of numerical methods.
Now you can see just how powerful it is right here. Let's try to find the square root of 100. We'll start with a totally wild guess, 50. One step of the recipe gets us to 26. The next gets us to 14.9. Just look at how fast our guess zooms in on the real answer, which is 10. By the fifth try, our guess is practically perfect. It's amazing.
Okay, let's grab the next tool from the box. This one's called interpolation. Imagine you've run an experiment and you have a few solid data points. But what about all the space between those points? How do you make an intelligent guess about what's happening there? How do you connect the dots?
Well, that's interpolation. It's all about creating a curve or a line that weaves through the data you know so you can make really good, educated guesses about the data you don't. But as you're about to see, how you choose to connect those dots, well, it matters a lot.
The most straightforward way to do it is to just draw straight lines between each point, kind of like a connect the dots puzzle. This is called piecewise linear interpolation. It's super simple, and it's really robust, meaning one bad data point won't ruin your whole curve. The only downside? The result is pretty jagged. It's not smooth at all. Or you could get a little fancier. You could try to fit one single, smooth, elegant curve that passes perfectly through all the points, and that can give you a really nice, clean result. But there's a huge danger here. The textbook warns that if just one of your data points is a little bit off, the curve can go crazy, becoming wildly oscillatory, creating these bizarre peaks and valleys that have absolutely nothing to do with reality.
So, okay, we've got these incredible tools that let us solve impossible problems and fill in the gaps in our data. It sounds like a mathematical superpower, right? But this power comes at a price. There's a fundamental trade-off that you just have to accept.
And here it is, laid out plain and simple. First, these recipes take tons of steps, so you need a computer to do the heavy lifting. And second, and this is the big one, the answers are never perfect. They are always approximations. They're just good enough.
Now, this inaccuracy comes in two main flavors. The first is called termination error. That's the error you get because you decide to stop the recipe. You know, like when we stopped the Babylonian method after 5 steps instead of 5 billion. The other one, round-off error, is different. It's like a ghost in the machine. Take a look at this number, just for a second. This is the actual number a standard computer gives you if you ask it to calculate the square root of 2, then square that result, and then subtract 2.
That answer? It should be 0. Obviously, it should be 0, but it's not. That tiny number left over, that is round-off error. It exists because computers can't store numbers with infinite precision, so there's always this little bit of mathematical dust left over after every single calculation. It's a fundamental limit of our machines.
But here's the absolute magic of it all. These good enough, approximate answers, with all their tiny built-in errors, are exactly what we use to build our entire world. They're not a flaw, they are the invisible engine of all modern science and technology.
Seriously, think about it. The weather forecast you check on your phone, that's a gigantic numerical simulation full of approximate answers. The sleek aerodynamic design of a car or an airplane wing, sculpted by numerical methods. The MRI scans that let doctors peer inside our bodies, the complex financial models that drive Wall Street, even the jaw-dropping special effects in movies. It all runs on this powerful math of good enough.
And that leaves us with a really fascinating, kind of philosophical question to chew on. We live in a world built by answers that we know are not technically perfect, and yet they're powerful enough to predict hurricanes and design spacecraft. So, if a good enough answer can do all that, what does it even mean for an answer to be truly correct? Something to think about. Thanks for tuning in.